So, hello, my name is Viktória Fördős. I'm a Cisco NSO developer, and I'm an Erlang addict. I've been active in Erlang since 2010, but before that I had a different background. I'm going to tell all about that, but now I'm curious about your background. So, please raise your hand if the first programming language you learned was BASIC. Okay. Was it Pascal? Right. Was it C? Okay. Or maybe Java? Okay, so I could say that the majority of the room was raised their hand when I said BASIC. Okay, next question. What was the first programming language you used professionally at work? Was it Java? Nice. Was it C or C++? More hands. Was it PHP? So I was a PHP developer before I went to the Erlang way. Or was it Python? Okay. COBOL? That was a joke. Oh, really? Wow. Sorry. That's really cool. That's quite a journey. Okay. So I think the majority of the room was C++, I feel. Okay, last question. So what is the language you use today at work? Is it Elixir? Is it Erlang? This is okay. Or is it something else? Right, so you will be the future Erlang Elixir developers then. That's really cool. Okay, so thank you. So as we saw, we have learned a lot of different programming languages, but mostly imperative ones. And how our brain works is that we try to, when we learn a new language, we compare that to the one that we already know. So we try to reuse the old, already proven methods. And I think after a while what we did is that we learned how to think imperatively. At least this is what I blame when I look at the first Erlang code I wrote. I was thinking imperatively, but coded in Erlang, and the result is pretty shameful. I don't want to show it to you. Right, but so the imperative paradigm, our old friend, we learned it, we use it a lot. So it has a lot of low-level details. We precisely describe how to execute the program. We are in full control. We focus on the how, so we focus on the control flow. And we have sequences, loops, abstractions, and we use all of these statements to mutate the state of the program. We even use this global system state to prove that our program is correct. Just check out the whole logic. Now, is Erlang an imperative programming language? No, I don't think so. It's functional, it's part of the declarative paradigm, meaning that all lessons we learn on how to solve problems must be learned again. And then in school we learn that it has high abstraction level that allows us quick prototyping and testing. We learn that there are no mutable objects, and honestly, I couldn't imagine how to write a program without mutable objects. But the thing is that these all sounds very nice, but we have no idea how to write those programs. This doesn't teach us. And then if we are lucky, we learn about lambda calculus. We learn about functions. We learn that we can create, apply, and compose functions. We learn that everything is a value. Therefore, there is no problem passing a function as an argument to another function. We learn about fixed point theorem. We either become a hater or a lover. It's going to divide us, but we are going to learn about it. So you know the thing is that lambda calculus is the key, but it is too abstract to notice that functional programming is all about data. It is all about data. It's all about data. We focus on the data. We focus on the what. We know. Remember that in the imperative paradigm, we focused on the how. Here, the how is completely irrelevant. It shall be seen as a black box. We just know what is our input, what is our output, and our goal is to shape that input data until we reach the output. For that purpose, we write data transformation functions. We take an input, and then we turn it into the output. We create, we apply, we compose those functions. We do that until we reach our goal, what is our output. We focus on the data. And now I would like you to look at this function application on the slide. Look at this sequence. So they are the same. Maybe the sequence is easier now for our exercise, because it has smaller granularity, so it allows you to see the things that I want to show you quicker. But since we focus on the data, we naturally see data flow. And we see data dependencies. And you know why is it good for us? Because we know which data can be computed in parallel. So look at this data dependency graph. It's from the sequence. Can you spot which two data can be computed in parallel? So it is B and C, because once the dependency A is ready, the computation can begin. So do we agree that focusing on data gives us big benefits? Yes. And does Erlang likes us focusing on data? Oh yes. Oh yes. It even gives us extra benefits. So concurrency is built into the language. We can compute data that is independent from each other in parallel. I would suggest you check out there was an EU project called Paraphrase, and they propose ready-to-use application skeletons for parallel computation. We can use the Erlang processes as computational units for parallel computation, and we should use them. Of course, one can say that an Erlang process is more like a reactive agent, it's smarter, it's an actor. But still, it is a computational unit. So this is what we should use. This is our building block. And how does this map to the I/O model? So the processes doesn't share anything with the outside world, but they communicate with it through signals. So the signals are your input and output if you are a process. The fact that in a process is running in which Erlang VM, that doesn't really matter most of the cases. So location transparency is built into the language. But now we enter the distributed world, and when we are talking about distributed systems, we know that things can go wrong and things will go wrong. Things will fail, network glitches occur, data center burns down, you name it, it will happen. But from our programming point of view, does this mean that we need to become defensive? No, we do quite the opposite. We embrace failure. And why is this good for us? Because that allows us to write a much cleaner code, to focus on the happy paths. Because like if you write a program, it's going to run on the happy path like 90, 80%, right? So then focus on the majority of the cases. And this will allow you to have a very clean code. This will allow you to see your data dependencies, to see your data, to see exactly what happens with it, removes a lot of ifs and cases, everything. And then what about the not so happy passes? Because that's going to happen as well. Well, in Erlang, you have a lot of way for error handling. In process level, you can use supervisors. You can still catch an exception and so. But you know what? Sometimes the easiest way to handle an error is that let it crash, because we embrace failure. Now I can summarize what I think thinking in Erlang means. So we focus on the data. We focus on the what. The how is completely irrelevant. It shall be seen as a black box. We just know what is our input and what is our output. For that purpose, we write data transformation functions that brings our data closer and closer to our goal. And we do see data dependencies. We see them, and that we use to compute things in parallel. We can scale our system horizontally, and we never go defensive. Quite the opposite, we embrace failure. Now, what I would like to show you is a good example of thinking in Erlang. You will see that the core concepts are there in the algorithm. So yes, it's an algorithm, but it is as well a patent. It was invented by my colleagues at Cisco, and the algorithm it solves a very, very ugly problem in scope of network management. So the algorithm is shipped with a product called Cisco NSO. Cisco NSO, in 3 sentences, it's a network operating system, it's a device automation engine, and it's a service orchestrator. Under services, we mean any type of services, really. So it can be creating a VPN. It can be adding a new branch office to your corporate network. It can be changing the access control list or redirecting a small percentage of your traffic to your Canary deployment. So literally anything, any rule that you can program into the network. Services, a service is an abstraction because it usually touches multiple physical or virtual devices. Right, now what's the problem that we solve? It's the service lifecycle management. So I will tell you first the traditional way. So the traditional way is you are going to end up with a very huge lasagna. It's a layered architecture. So in the bottom, you are going to have a lot of CLI and SNMP scripts. And then, because this is how you talk to the network devices. And you will need to implement it for every different device. Then on top of that, you will have a big, big chunk of error handling, but a really big one. Because when you try to do network-wide transactions, and then something goes wrong in the middle, then you will have a lot of strategy how to recover from it. But you don't want to leave your network in an inconsistent state. On top of that, you will have the business logic, the glue, the service implementation, where you are going to implement the create, the update, and the delete. Because you want to create a service, you want to modify it, and you want to remove it from your network. And to be able to talk to this big lasagna, you are going to have a northbound API that you are going to do. Now, imagine what happens when a new parameter comes into the game. Like, from now on, we are going to label customers that, okay, she is a GOAT customer, so now the bandwidth should be bigger for that VPN leg, or you name it. Now, in that case, the change will bubble down from the top, and you will need to change all layers. Or what happens if I change one of my routers in the bottom? Then that's going to bubble up. So it is really error-prone and cumbersome. So you would like to do something else. And what is this? It's the NSO way. So what NSO needs is 2 things. One is a service model. It's written in Young. NSO doesn't understand it. It sees it as a black box. It just uses it to generate you the northbound API, and it is going to take the input and the output. Okay? And then Another thing what you need to do is a data transformation function. What is to, you need to implement, how would you deploy your service from scratch? Nothing else, okay? It's only the create. And then you are going to get in return the create, the update, the delete. You are going to get error handling, and you are going to have Northbound API. How is that possible? So the algorithm is called the FASTMAP algorithm. So here comes the create. The service input parameters arrive, so the intent is arrived to NSO. It takes the service input parameters, the user create code, and the view of the network that is stored in its very strong, consistent database. And then in one big transaction, we apply the create code on the current device configurations. From there, we calculate the effect of that create code. And then what we can as well do is to calculate the reverse effect. Like, what do I need to do? So I went from A to B, and how can I go back, right? Okay, so the reverse diff set is going to be stored as undo information, and then the effect of the real create is going to be calculated as minimal configuration changes that we are going to push to the devices. We do that in a transactional fashion. So NSO takes care of being sure that the network is consistent, and if an update fails on one device, then we are going to roll back or apply different strategies. Our goal is to converge the network as quick as possible to a consistent state. Okay, so the delete. So the intent arrives that we need to delete this service. What NSO does is that it looks up the undo information that it already stored about the create, runs that undo information on the current state of the network, captures the effect in one transaction, calculates from there the minimal configuration changes, and then that is what we push to the devices in a transactional fashion. Please notice that there was no user code involved, so you got the delete for free. Can you guess what is the update? It's a function composition. It's a function composition of create and delete. So what we do is that in one big transaction, first we apply the reverse diff set. We first apply the undo information on the current state of the network. Then we run the create, the user code on this state, so the user code starts clean. It doesn't know about any changes, and it doesn't need to handle it, nothing. Then we capture the overall effect of these two operations. From there, we can calculate the minimal configuration changes that we will push to the devices in transactional fashion, and we calculate the new undo information. Nice and simple. So we have the reactive FASTMAP algorithm, but I see that I'm running out of time. This is only about, we had the FASTMAP algorithm, but now imagine that this is a process, and external stimuli send signals there, and then that's going to make it to converge and do further steps. But the real message that I want you to memorize and take away from this talk is what is thinking in Erlang. Because it's really about the data. This is our focus. We don't care about the how. We really like focus on the data. We know what is the input, what is the output. Our goal is to shape our input until we reach the output. We feel data dependencies. It is in our blood. So we do compute things in parallel. For that, we use processes. And we do scale our system horizontally. And we never, ever go defensive. We embrace failure. Because that allows us to focus on the happy path, to see our data. And yeah, that's it. Thank you very much.
Do you have some question for Viktória? Okay, I do. What is the option, what is the situation that you think that maybe don't think in Erlang would be the answer for that? I mean,
Don't think in
yeah,
Erlang.
yeah, like the opposite. I'm speaking by the devil right now. Like.
Well, I mean, you can always choose. So it's based on use case. So, okay. But well, that's coding in Erlang. What I was thinking about. So I wanted to say that for number crunching, I wouldn't use Erlang. But I think that thinking in Erlang is a way of problem solving, where you are focused on your starting point, and you know what is your end, the desired state, and you can be bold, and you can try to go there in one step, or you can go there like in multiple steps. But you need to try to get closer and closer there. Yeah.